Okay, this is calculus class, so we're going to call this Calculus Jeopardy.
Clever. Wow. Wow.
I would never have come.
And so here's I'm going to give you the answer, right? And you have to give me, I'm going to give you the answer to the question, and the correct answer from your perspective is going to be the question, right? You have to answer in the form of a question. So here's the answer.
Yeah, you're right. It's a little bit.
Yeah, I know. You probably, hopefully you've gotten used to it by now.
I have. I don't know if they have.
I'll give you a second to think about this too. Hang on a sec here. Okay, you got it. All right, yeah, buzzer first here. I think was the first buzzer. Okay, so what do you got?
What is the derivative of x cubed plus n?
Okay. What is x cubed?
The derivative of x cubed plus n.
Oh my, that's pretty good. So the derivative is 3x squared. I could say what is the derivative of. I'm just going to say what is.
Yeah.
X cubed plus
n.
N. What's n?
Any constant.
Okay, I'm going to call it C.
Okay.
C for constant. That's pretty good. That's Calculus Jeopardy. Okay. Wow, what you just did, by the way, is called an antiderivative. Antiderivative is literally just the game of Calculus Jeopardy, right? We're going to work backwards, and we're going to try to determine what function would we differentiate to get this result, right? Let's try one more round of this. Think for just a second here. Okay, Paige.
What is cosine x?
Oh, very good. What is cosine x? Outstanding.
Can we get buzzers next time, maybe?
You know, we really need buzzers, don't we?
Wait.
Okay, so so you get the idea, right? We can. Okay, cosine x is. Let's talk about that. Cosine x is a correct answer. It's a correct answer. What's another correct answer?
Plus c.
Okay, I could say cosine x plus c. I could say cosine x plus 5. I could say cosine x minus 10. But if I put that plus c, how do you guys know about the plus c?
I heard it from Lucas when I went to go to the college.
Well,
On a college trip.
Okay.
He told me about
Okay, I
it.
wonder where that came from. That's the first time that's ever happened. Somebody said
I was talking
x
about
cubed plus a constant. Normally, what people would say here, normally, every other year for the past 24 years or whatever, I've always just gotten the answer x cubed, right? And that is a correct answer. And then I've asked people, well, what's another correct answer? And at first they have to scratch their head a little bit, but yeah, when we differentiate, remember that when we take the derivative of a constant, what is that? 0, right? And so we have to account for the fact that there could be a constant attached to that x cubed, right? So when we say something like this, when we say something like x cubed plus c, what we're really saying is there's an infinite number of possible solutions, and in math we have a very specific name for that. We call that a family of curves, right? And all of those would have the correct answer if I differentiate of 3x squared, right? Let's take a second and let's think about that in, well, maybe, the Jeopardy thing is a little bit tedious. First of all, we have to come up with some you know, with some, maybe a more concise, efficient way of playing Calculus Jeopardy without having to write all that text down. That's not very mathematical. I don't like doing that stuff. What if we wanted to say something like instead, I'm going to say y prime equals 2, or dy dx equals 2, something like that, right? That's an easier way of saying the derivative is 2, and then what would the result be if we played Calculus Jeopardy?
Y equals 2x plus c.
Okay, so then that tells us y equals 2x plus c, right? So if we were to do a graph, and I'll just pull up Desmos so I don't have to do this by hand. If we were to do a graph of that family of curves, what's it going to look like? So I could graph y equals I don't know where that, I'm just going to do a new. So we've got y equals 2x minus 2, let's say. Zoom in a little bit. Y equals 2x minus 1. Y equals 2x plus 0. You get the idea. What do they look like? Parallel lines. Okay. And so if I want to look at any of those lines, that's a family of curves. If I calculate the derivative of any of those, what am I going to get back? 2, right? Okay, does that make sense? Okay. Each one of these lines is what we call a trajectory in the family of curves. There are an infinite number of trajectories. I just picked 4 of them, right? What if we pick something, let's go maybe a little harder example. Let's go back to the one you did just a little bit ago, right? You already told me that if y prime equals 3x squared, then what's y?
Yeah, x cubed.
X cubed, good, plus c, right? And so I could get the same, you know, I could get the same kind of a graph from that, only this time, oops. Only this time, instead of 2x, I've just got x cubed. So I think I can just cut and paste here. What do you notice in common? If we zoom out a little bit, what do you notice in common here? If we talk about a family of curves like this, I mean, describe that. What are the trajectories all, what do they all seem to be relative to one another? They're, okay, in this case we can't really say parallel. I mean, I guess we could. You could argue parallelism for any value of x that we pick, a specific value. Let's go further. Nick, you said that. Tell me what's going on. You tell me, I won't tell you.
You said parallel at 0.
Parallel at 0, for example. Yeah. Okay, so we could say, it's like cat chasing its tail. There. Oh. What the heck? Where's my... Can you guys help me out here? What am I doing wrong? I just want to be able to...
What are you trying to do?
Oh, there we go. I'm trying to be able to, yeah, I want to be able to see, something's not right here. Oh, that's weird. This has never happened before. That's supposed to let me see my desktop, which it's not letting me do. That's better. There we go. Okay, that's better. Okay, so yeah, the idea of parallel, Nick had an idea here, good idea. At x equals 0, the tangent lines are all horizontal, right? And so they are all parallel.
I guess at every x value.
At every x value. Yeah, so at x equals 1, if you look at the tangents at x equals 1, they're all parallel, aren't they? That makes sense, right? If the derivative has to give us back, the derivative corresponds to the slope of the function. If they have to give us back the same value, right, then for any value of x that we choose, and that's what a derivative does. And I think what this means, if we're saying that y prime equals 3x squared, well, another notation for that would be f prime of x equals 3x squared. That's telling us that for any input value, this is the function that's going to calculate the slope, right? So we would, if we think about it, we would expect this kind of behavior, wouldn't we? How would you describe the orange graph related to the green graph? For any point, they're parallel, but could I turn the green graph into the orange graph very easily? What would I do, Richard? Zoom, well, okay, I mean, I could zoom out. If I zoom out, you mean they're all going to eventually look pretty similar. Okay, but if I were to zoom in, I would see that they are different. What's the one thing I could do to the green graph to make it identical to the orange graph at any scale? At any shift it where? Yeah, so these are just vertically offset, aren't they? Right? They're just vertically offset. So when we look at a family of curves, when we take an antiderivative like we're doing, and we get back an answer that's a family of curves, and that's what this C means, isn't it? That C could be anything. This is just going to be an infinite collection of trajectories that are stacked up vertically. They're just vertically offset, right? Okay, so what you just did, by the way, without knowing it, was you solved your first differential equation. Okay. These are all examples. This right here is a differential equation, which is nothing more than an equation involving one or more derivatives, right? So here we've got a y prime. That's a derivative. When you solve a differential equation, the solution is always going to look like the function that you would differentiate to create this equation, right? Okay. So we're calling that process anti-differentiation, right? This is what we're now going to call an antiderivative, is if we solve a differential equation and play Calculus Jeopardy, what's the function we can differentiate to get this derivative? Later on in life, I know you'll all keep going with math. Later on in life, you're going to take a series of courses in college where the focus is exclusively on solving harder and harder differential equations. Differential equations that involve multiple derivatives at the same time. Differential equations that involve derivatives with respect to different independent variables at the same time. And there are techniques for dealing with all that stuff, right? We're just starting to scratch the surface with what we're talking about today. Okay, what if we do something like this then? Let's take a different kind of a differential equation. Let's take something like, let's say y prime equals 2, but we're going to attach some additional information to that. We're going to say that our curve has to go through the point must go through the point 0, 2. Okay? So why don't you close that up? So what's the antiderivative? Play Calculus Jeopardy.
Plus 2x plus
Okay, 2x plus c. You already told me. Good.
c.
Okay, so if this function has to go through the point 0, 2, what's that doing? What's it? It's specifying c, isn't it? Right? It's specifying c. If I know that when x is 0, y equals 2, that's going to lock down the value of c, because there's only going to be one value of c that's going to make that happen. So what if we plug that stuff in? We're going to get 2 equals 2 times 0 plus c. So what's the value of c? 2, yeah. And so this gives us, all this stuff right here, gives us the specific answer, y equals 2x plus 2. Okay, if we say that this is what we call a general solution, right, because it gives us the whole family of curves. So this guy right here, if that's a general solution, then we say that this guy right here is a particular solution. What does that correspond to in terms of our picture then? It's a different picture, but what did we effectively do? By specifying a point that the function has to go through, like just for example on this graph here, different function, but it would be equivalent to saying, I want the specific trajectory that goes through the point, how about 1, -1. Only one of the trajectories is ever going to go through that point. Can any of the trajectories ever cross? They can't, can they? Right? If they're functions and they don't overlap vertically, when they're offset vertically, none of these trajectories can ever intersect the other, and so only one trajectory is ever going to go through that point. And that's going to be the particular solution that matches this point, right? Okay? All right. Okay. So, let's make this even a little bit more formal. And this is just notational stuff. I'm not really adding anything new to this. But if we say something like, if we go from dy dx, so our derivative equals f of x, for our differential equation, if we write this in differential form, okay, so there's our derivative, what's that going to look like if we write that in differential form? We just talked about differentials. What did that mean? Right now, this is telling us the rate of change of the output with respect to the input is going to be given by a certain function, right? But remember, in differential form, what we wanted to do is we wanted to compare the values of the output to the values of the input for a small nudge of the input, right? So what would I do? Well, kind of, but like, I mean, we did stuff like, we had like a sphere, right? We wanted to find propagated error for a sphere. We said that dv dr equals, what's the derivative? If we start off with v equals 4/3 pi r cubed, what's dv dr? 4 pi r squared, right? So that's the rate of change of volume with respect to radius, but if we wanted to write this in differential form, we were interested in knowing how big of a nudge in volume are we going to get for a nudge in radius. Okay, so we said something like this, right? We said dv equals 4 pi r squared dr, which told us that if we're going to tweak very slightly the value of radius, then we could expect this function to determine how much, what's the corresponding tweak going to be in volume itself, right? So up here, if we want to take something where it's not specifically representing volume, it's just some generic function, y is a function of x, then if we write this in differential form, it just looks like dy equals f of x dx, right? Okay. Does that make sense, first of all? Give me a thumbs up, thumbs sideways, thumbs down. We're good? Okay, good, all right. So then, if we want to figure out what's the function from which a derivative occurs, here's technically the way that we say this. We would say, if this is true, if we're starting off with the differential equation, dy dx equals f of x, then y is equal to the antiderivative of this function, okay? Here's our notation for that. We use what's called an integration symbol, okay? And what goes inside is the differential form of this derivative, okay? So this is the integral sign.
Is it just kind of like an
We
S?
call this. And what that is, it's kind of like an S. What it is, it's Greek. It's a lowercase sigma in Greek. This is, you might remember from pre-calculus when you added up sums, and this is going to be very cryptic, and you're not going to see this connection now, but in about a week and a half, this is going to be amazing. You're going to see this connection to what you did last year. When we did a summation last year, when you're adding up a series of terms, right, you use sigma, right? For example, if we want to add up, let's say we're going to add up I as I goes from 1 to 10, what would that represent?
Remember that's
Did we just do this? Oh, you guys didn't do this.
Yeah, that's the one thing we didn't do.
Oh, yeah. Okay, so, all right, so, never mind. We'll cover this next week. We'll go through this stuff very briefly, and then you'll make the connection. That's right. Okay. So, that's right.
I guess we all do.
There we go, okay. So, this is how we write this, right? Here's the function that we're trying to play Calculus Jeopardy with. And the answer that we get from that, we're going to call capital F of x. You can see that the small f and the capital F are related by this process. This is what we call the antiderivative, okay? In other words, this is the that's the antiderivative, right? That's the function that we would differentiate to get this result. Okay, this part in the middle here, we're just looking at the anatomy of an antiderivative. That's what we call the integrand. So that's the function itself. In our previous examples, we would have said that 2 is the integrand, because that's the function that we're playing Calculus Jeopardy with. And the solution in general form was 2x plus c, right? Okay, and then this just merely represents, for now we're going to call this the variable of integration. Integration and anti-differentiation are synonymous at this point, right? So that's how we express this. If we want to look at one of our previous examples, we would have said, what? What's the answer to that? This is the function that we're trying to play Calculus Jeopardy with. Very good. Okay, that's how we write that process in calculus. This says the antiderivative of 3x squared dx equals x cubed plus c. Okay? Right? So this is the format we'll be using. It'll make a lot more sense when we start to look at the true meaning of what an integral looks like. What's this one?
Plus C.
Very good, right? So the antiderivative of secant x tangent x is secant x plus c.
Does C need to be uppercase or lowercase?
Okay, good, very good question. The C is always, we always write it uppercase. Yeah, capital C. In every calculus textbook, if you look at tables of antiderivatives, it's always written as a capital C. Okay, we'll go a little further with this tomorrow.